Good morning.
Good morning. O microfone. O Bruno, talvez na palestra dela, o microfone do canto aqui ficar aberto, porque os pelo tá direto. Mas tá tudo? Não, tudo bem. Tá funcionando. Sim. Não, tá funcionando bem, sim.
Ela escuta também limpinho também.
Sim, tá ótimo.
So how are we doing this morning? Hello. Hello, class.
All right. So welcome back, everyone. And let's just start now the third talk by Leah. Continue learning about the Leavitt graph algebras.
Okay, so actually today, first half an hour should be fun. I hope it will be for you too. So we are just going over more examples, and then actually we're going to compute a Grothendieck group, which is very, very nice and simple. So that also should be a fun part. After that, we will start talking about graded rings, because that will help us understand the graded part of that conjecture. So if you are looking at the notes, we are still at the end of lecture 2. We are a little bit behind, but that's okay. we'll get there eventually. So let's see where we stopped last time at the end of the day yesterday. So let me just remind you what we did. We computed a Leavitt path algebra of this graph here. And then we also computed a Leavitt path algebra of this graph here. And then we talked a little bit how identity of Leavitt path algebra is sum of vertices if a set of vertices is finite. So today I'm going to go a little bit further with examples. We are going to see what if that cycle maybe has length 2, or what if you have something leading to the...
Excuse us, Leah, you are writing very in the top, then the camera is not catching the
Oh, okay. So because my camera is showing this, so up to here, you're fine?
Yes.
Up to there. So just the first line. Okay, let me actually, so above that line, I shouldn't write, right? Behind this line, I shouldn't write, or even lower.
The top one here. You can go all the way
top
to the
one. Okay, good. So the first example that we did yesterday was this one, right? Then the second was this one. Today we are going to go a little bit further. What if you have a cycle of larger length than 1? What if you have paths leading to a cycle? And then we are going to go after that to what if you have maybe something like this. So cycle with exit, that is another cycle. So you see all these are going to give us some interesting algebras to talk about. So let's first see about this one here. So here you have, what do you have? You have U and V, right, as vertices. And you have E and F as edges, right? And then you have EF, and then EF, and EF. So actually you have infinitely many paths of infinite length, right? And let me actually remind you, Leavitt path algebra of this graph here. We said that it is isomorphic to Laurent polynomials over X, right? So it turns out that this algebra here can also be made isomorphic to some kind of matrix algebra over actually Laurent polynomials. So that's why I want us to understand what Laurent polynomials is, what this algebra is, because I'm claiming that this one here can be related to that one, and actually this one here too. So Leavitt path algebra of this graph here, let's call it E, is going to be isomorphic to matrix algebra 2x2 matrix algebra over Laurent polynomials. So let me tell you where Laurent polynomials are coming from, and let me tell you where the 2 is coming from. So what you want to do, you want to pick one of these two vertices, u or v, doesn't matter. Pick one of them, right? So pick a vertex in the cycle. So let's pick u, for example. Then I want you to count the number of paths that end at u, the number of paths ending at u without counting the whole cycle. So what paths do we have ending at u? We have u and we have f, right? F ends at u. And then if I want any path of length larger than that, then I will actually have to include the whole cycle. So that doesn't count anymore. So you see, there are exactly 2 of those paths. So you see, this 2 goes down in the size of your matrix algebra, right? And then it's Laurent polynomials because you have a cycle. So actually, I want you to now compare. Let me now do this as a 4. I want you to compare this example here. Let's call this one u. So let's count how many paths we have ending at u. So the number of paths ending at u is 2, because those 2 are u, right? And if this edge is called e, then it's e, right? And if we understand that this example here gives us pretty much 2x2 matrices over K, then you will probably believe me, and if not, convince yourself of that this Leavitt path algebra here is isomorphic to M2 of K, right? So I want you to think 2 ways to get to that sink. Either I'm already there, or I have to take this edge here, right? So there are 2 of those. So that's significance of those 2. This is a sink, not based on any cycle. So that's why here I have just my base field, not Laurent polynomials. So you see, that's kind of what we have going on here. And before I give you the general formula of how to handle graphs of this sort, let me just now go over this one that I just erased, right? So let's call it example number 5. So let's say that we have something like this. And I'm trying to figure out this Leavitt path algebra as some type of matrix algebra over something. So what am I doing here? I pick a vertex in a cycle, where here I don't have a lot of choices. We have just one vertex in this cycle. So let me pick that one. Let's call it u. And then we count on how many ways I can get to that cycle without including the whole cycle. So there are 2 ways to get there, right? 2 paths ending at u, and if this is called e, then e. And I'm not counting f, that also ends at u. But remember, if you have cycles, then you're counting how many paths without the whole cycle. So that would be just these 2. And then since we have a cycle, not a sink, I will have Laurent polynomials and not the just the K. So you see, this gives you a pretty interesting class of graphs. So let me now give you the whole generality of this story here. Let me erase these examples now. So a graph E is said to be, I call it no exit. People sometimes use the longer name, saying E satisfies condition NE, and N is for no, E is for exits. So shorter, it's just no exit graph for me. So E has no exit. If every cycle of E has no exits, not much of a definition. And what is an exit of a cycle? So what is a cycle, by the way? I think that we mentioned that yesterday, but let's hear that definition again. So this is a closed path. So I can have more than one edge, right? So think closed path. And then I cannot have different edges originated from different vertices. So I want it to be like simple in some sense, right? So just think closed paths that are in some sense, simple. So that's a cycle, right? And what is an exit? Exit is an edge leading out of it, right? This would be an exit. So if you have a no exit graph, and if maybe E is also finite, then its Leavitt path algebra is as simple as these examples that we covered. So it is always just a bunch of matrix algebras over either Laurent polynomials or over K itself. And the formula for it goes as follows. So it is a sum of matrix algebras over K. So how many of these matrix algebras you have here? As many sinks you have. So you are going from 1 to number of sinks. And here you have Ni. So what is this Ni? It is number of paths. Let's call it like this, number of paths ending at ith sink. Okay, and then you can also have cycles. And these cycles, they are always in a way dead ends, right? Because they cannot have exits. So let's now go from 1 to number of cycles. And these matrix algebras, let's say that their sizes are mj, are over Laurent polynomials. And this mj is number of paths ending at selected vertex of that cycle, right? Remember how when we had this example here, we said we can pick U or we can pick V. So we have to make a choice here, pick one vertex of the cycle, and then some arguments should be made that your choices don't matter. So in the previous example, I picked U. What happens if I pick V? I should better end up with the same algebra, right? So that's also some convincing for you to do, right? Try to figure out, well, why would that be? And I can tell you, let's just first finish writing this formula, and then I'll tell you what material may be helpful to you. So this is number of paths ending at a selected vertex of the cycle. Not very good use of board today here. Without counting the whole cycle itself. Okay, and the good reference in convincing yourself that these choices here don't matter is the first paper. Well, actually, you know what? In my notes in the back, you have a book on Leavitt path algebra, so that contains more detail. I think it's number 1 in the list, right? So, so there you can find more details about this formula. And let's just do one more example. Let me now take some graph that has both sinks and exits. So let's maybe have something like this. So I have one path to a sink, and then double path here to a cycle looking like this, right? So pretty much this is how these no exit graphs look like. Every path, if you continue on every path, you are eventually going to end either at this type of dead end, sink, or this type of dead end, you know, kind of like you can just go around, you cannot exit anywhere. So that's why they're going to have such a simple structure, right? Because after all, not that many things happen in these graphs, right? If you start continuing the paths, either dead end or some type of like loop that you cannot leave. So let's count. Let's see the matrix representation, the matricial representation of this Leavitt path algebra of this graph. So how many? Here we have one sink and one cycle, right? So you are going to have two terms. Something over k corresponding to that sink, and something over Laurent polynomials corresponding to that cycle here, right? How many paths we have here ending at this sink V, right? We have path of length 0 and we have path of length 1, so this will be 2, right? So 2 paths to this. Here we have to decide, do we want to count paths to here or do we want to count paths to there, right? I want you to do it both ways, and then you will see that you will end up with the same number. So let me maybe pick V here, right? So how many paths here? I have V. Let's call this E. Let's call this F. Let's call this G. And then I have E, and I have F, and I have G, F, and that's it, right? All the other paths would contain the full cycle, and I don't want that. So we have 1, 2, 3, 4, so this will be 4. So then you have, for no exit graphs, you should be fine with computing them. So if you're looking for more examples, here I have more no exit graphs on page 10. So try to do, again, a little homework. Try to do, they're all no exit. There are 3 graphs. One kind of looks fancy. And then when you sit down and when you count how many paths, and then when you write your matrix algebras, then you will feel empowered. Oh, I can handle this fancy graph here. So this should boost your confidence to continue with this story that I'm telling you. So are we good with no exits? Are we okay with this example? So let me now show you something that is not no exit, that is different. Because after these examples, you may think, well, you know, so far all that we have seen are matrix algebras and Laurent polynomials, or maybe matrix algebras over Laurent polynomials. So is it all that there is, right? Why do we need Leavitt path algebras when after all it's all matrices? So of course it's not all matrices. So let me now give you a new example that is not actually going to be isomorphic to matrix of any like commutative ring or matricial algebra of any commutative ring. It's not on the table for this graph. So let's talk about this one here. So this one here is not no exit graph because this loop here has this exit there, right? So this story that I just told you about no exit doesn't apply for this graph. So let's see what our CK1 and CK2 are giving us, right? this has one and only vertex, so I will already call it 1, because remember, 1 is sum of vertices, and if you have just one vertex, that's your 1 in your algebra. So let's call this 1, let's call this E, let's call this F. CK1 is giving you that E star E is 1 and that F star is 1. Just to remind you how CK1, what CK1 tells you, it tells you that E star E is range of E. Well, I mean, here there is just one vertex, so this is range and source of everything there is here. So pretty much this tells you that like E and F have left inverses, right? E and F have left inverses. What is CK2 telling me about this graph here? CK2 is about regular vertices. Well, we have just one vertex here. It emits finitely many edges, 2 of them. So that CK2 applies for that vertex. And then that CK2 relation is telling you that it is E star, sum of these elements for every edge V emits. Well, it emits 2 edges, so there are going to be 2 such terms. So these are your 2 terms. So you see, this algebra is interesting because E and F, they have left inverses, but they don't have right inverses. These left inverses are not right inverses for these elements. So that's already kind of interesting, right? And this actually Leavitt path algebra is such that when you add it to itself, you get isomorphism with the original algebra. So this algebra is such that 2 copies of it are isomorphic with 1 copy of it. And how can you be convinced of that? Let me give you actually the isomorphism and the inverse. So here, if you take 2 elements from here, ordered pair, you can graph it to EX plus FY. And if you have an element in here, you can graph it to E star X, F star Y. So write down the details, and you will see that these 2 are mutually inverse to each other. So that means that they are bijections, and convince yourself that they agree with algebra operations. So that also is fine, right? So this is an example of a ring. Remember that one of our early examples, when we were just computing the Grothendieck group, was actually a ring such that R plus R is isomorphic with R, right? That was one of our early examples. So you see, studying these types of rings was interesting because they don't have a well-defined rank or dimension, right? Because of this property here, right? Because this is kind of 1-dimensional, this is kind of 2-dimensional, and if these are the same, that just it gives you that, you know, your concept of dimension is all, you know, weird and and iffy for this type of ring, right? So you see, that's why people studied these type of rings even before they start studying Leavitt path algebras, actually way before Leavitt path algebras. And then when this Leavitt path algebra or graph C-star algebra of same graph was considered, that that related Leavitt path algebras with these rings that have this property here, right? And in fact, Leavitt, now we come to the name Leavitt from Leavitt path algebra. He defined such an algebra over K, not via graph, but via just some like 2 axioms that almost look like CK1 and CK2. And then he showed that this is more than just an example. It is universal example of such a ring. So, so this Leavitt path algebra is also universal example of such an algebra. So imagine that R is not just a ring, but it's algebra over K. Then you can find a homomorphism from Leavitt path algebra to this R. So this is universal example in this sense, right? So any other algebra with this property kind of in a way contains some type of copy of this particular Leavitt-Path algebra in itself. So this graph here is called a rose with 2 petals. And that's why I have, if you're looking at the notes, a picture of a rose, not real rose, right? But another rose. So, so the same story goes for roses with more petals. So if you have, I don't know, 5 petals here, then you're going to have a Leavitt-Path algebra that on 5th powers is isomorphic with the algebra itself, right? So you see this is certainly different than previous examples. And you have more examples of different graphs on page 11. For example, this Leavitt-Path algebra of this graph is also pretty famous. This is called Toplitz's algebra. So you have one loop with an exit. So it's not no exit, right? It doesn't look just like those matrices. I don't want to go over all these examples because I would rather start telling you about how to compute Grothendieck group. But there are some interesting examples on page 11. You have another one with infinitely many, with an infinite emitter. So far we haven't seen any infinite emitters. So you have what Leavitt-Path algebra of this graph is on page 11. So now that we have seen some Leavitt-Path algebras, let's actually compute. Let us compute Grothendieck group of a Leavitt-Path algebra. So that's next on the agenda. Now we are kind of connecting these 2 things that we have been talking about. First, we talked about Grothendieck group, then we talked about Leavitt-Path algebra, and now we are connecting these 2 things together. So I'm going to tell you this story only for row finite graphs. What does that mean? That means no infinite emitters. Just for simplicity. So the story is known for all graphs. I mean, it is known how to compute Grothendieck group of Leavitt-Path algebra of any graph. But there are more, axioms involved and more like fine tuning. So I will tell you the story just for row finite graph. And if you're curious, you can then, knowing what you will know, you can easily generalize to all graphs. So assumption today and maybe half a day tomorrow is going to be that your graph is row finite. Okay, so first thing that you want to do before you compute K0 is you want to compute this monoid of isomorphism classes of the algebra. And then if you remember, that kind of embeds, or somehow you can get a completion of it, and then you can get a Grothendieck group. Right? So remember what this was? This was finitely generated isomorphism classes of finitely generated projectives. And then you somehow complete that to a group, and then you have Grothendieck group. So it turns out that for Leavitt-Path algebras, these 2 things don't depend on algebra structure. They depend only on graphs. So what we are going to do, we're going to define a monoid called ME, and this is called a graph monoid. Graph monoid because it depends only on graph. It doesn't matter what your K is. For every K, it will be the same thing. So this graph monoid is going to give you this, and its Grothendieck group completion is going to give you the Grothendieck group. So this graph monoid actually appeared very, very, very early on in the history of Leavitt-Path algebra existence. So Leavitt plus algebras are introduced in 2 papers. One of them featured the monoid already. You see, because people were trying to compute some type of monoid that would satisfy certain properties for another conjecture that that people were trying to figure out, and they were also trying to kind of get to the algebra that would give you the same monoid, because this monoid is shared with graph sister algebra. And graph sister algebra, as we talked about yesterday, is fancier algebra than only Leavitt plus algebra. So that's why people were interested into getting to this monoid only based on graph. So pretty much, let me give you the monoid. So this is free abelian monoid. With generators, isomorphism classes of vertices. So you can say, I can take vertices and I can take elements and index them by vertices, right? And I'm going to write, instead of some new notation with vertices down here, I'm going to put vertex in this bracket, because I want you to think that this is finitely generated projective, defined by, generated by vertex, right? So if we are talking about right modules, then I'm going to put algebra on the right, and then this here is finitely generated projective, because if I have, let's for a moment say that I have identity, that my E0 is finite, then I have that V times the algebra plus 1 minus V times the algebra is algebra, right? So that's why this is a direct summand of this free. That's why this is finitely generated projective. So these are my generators, right? Think for every vertex, that kind of is your generator. You can really think vertices are generators. Okay, so these are your generators, and then what the relations are. So for every regular vertex, you want a relation that will look kind of like CK2. So let me first give you the relation, and then I will relate it with CK2, and I will actually talk about why this relation holds and why this relation and not some other relation is used for definition. So this element, your generator, if V is regular vertex, is equal to the sum range of E, where E is in S inverse of V. And let me write down CK2, just so that we can see this relation in parallel with CK2.
Excuse us.
Uh-huh.
How do we know that these projective modules exhausts all the possible projective modules over LK?
That is a very, very good question. That is a really good question. So somehow, because you're, so this is not a straight answer. I mean, we would need a lot of, a lot of other background and some proving to do to show what you said. So, so what you said is true. The answer is yes. This is enough. This is exhaust everything. But to see that that is so, we need way more, knowledge and some proving to do. So I cannot squeeze that answer in this lecture today. But it is true. If you want more details, that paper that I mentioned that introduces this concept is by Ara Moreno Pardo. And the answer is there. I want you to think that somehow, because we are after all based on graph, that's why vertices are enough. So, so let me write CK2. which is saying that V is the same sum over the same set, right? Remember, if V is regular, that means that this set is finite and non-empty. And here we have E star, right? So first of all, you know, that kind of looks like this, right? So let me now show you not the answer to that question, but let me show you why this relation holds in monoid of finely generated projectives. So I will not show to you why this is the only thing that holds, but I will show you why this holds. So why this holds? So let's start with V. Let's use CK2, right? V is regular, so we can use CK2. How do we add things in monoid, right? Because I want you to think that this is some type of direct sum of finely generated projectives. This is also a projection, right? So it's idempotent. So it corresponds to finely generated projective. So how do we add stuff? Well, we add that this is kind of like direct sum of these finely generated projectives, and we add them up, right? So this is pretty much how your addition in monoid is defined, right? And then somehow, if we can switch these around, then CK1 tells me that that would be range of E, right? So Leavitt path algebra is far from commutative in most cases. But if we are looking at finitely generated projectives, then we will have that this finitely generated projective and this finitely generated projective are isomorphic, and left multiplication by E is the isomorphism. So you see, that's why in that monoid of these isomorphism classes of finely generated projectives, we can switch these two around. Because after all, we are just looking at isomorphism classes, and these two things are isomorphic. So going from here to here is because this is an isomorphism. Again, try to convince yourself, why would this be true? Why is she telling us this? Try to think about how, you know, and why this would be equal. I mean isomorphic. And then CK1 is telling you that E star E is actually range of E. So that is why this relation holds in the monoid of finitely generated projectives. And the argument for why this is the only relation that holds in this monoid is longer, but you know, at least we understand it. We understand why this holds. So now let's actually compute Grothendieck group of finitely generated projectives. Let's see how what K0 of some Leavitt path algebra is. I'll erase this. I will maybe just leave that relation somewhere in the corner so that we have it in front of us. So V is equal to some range of E, where E is in S inverse of V, right? That's my defining relation. So the first example, something super simple. So let's just take one vertex, no edges, right? This is the simplest graph that exists. So let's compute Grothendieck group of this simplest graph. So, okay, how many vertices? One vertex, right? It is not regular because it doesn't emit anything. So there is no relation. So there is one generator. Let's call this V. So one generator, V, no relations, because this applies only if your vertex emits at least one and finitely many edges, right? And if it doesn't, then there are no relations. So if you think of this V, one and only generator, as some type of one, and I don't want you to think that that's kind of identity, because we are not multiplying here, we are just adding stuff, right? So if that is your, like, you know, generator, one and only generator, what is then this monoid ME? It consists of 0, right? It's a monoid. There is a neutral element for plus, which is 0. Then we have that one and only generator, and then we have 1 plus 1 and 1 plus 1 plus 1, because after all we can add, right? So all these elements are there. And then we clearly see that this ME consists of 0, 1, 2, 3, 4, 5, 6. And when we complete it to a Grothendieck group, then we have that this is isomorphic with Z, right? Because when we complete 0, 1, 2, 3, 4 to group, then we have to add the inverses, right? So this is -3, -2, -1, 0, 1, 2, 3, 4, right? So that's exactly Z. So this simplest graph has this very, very, very first example of Grothendieck group that we have seen. Now let's see another graph, and let's compute a Grothendieck group of that. So let's not go overboard still. Let's just go one step further. Let's take now this loop. So there is still one generator, because I still have one and only vertex. And I now have a relation because this does emit edges, right? Finitely many of them. So one relation, and the relation tells me that V is equal to V, right? Because range of that one and only edge that I have here is V again, right? So V is equal to pretty much range of that edge, and the range of that edge is V also. So you see, we do have a relation, but it's not much of a relation because it doesn't tell us anything new, right? So this one relation is just saying that 1 is equal to 1. Well, that, you know, is nice, but it doesn't add anything new to the table. So what we still have is that our monoid consists of these elements, and so its Grothendieck group is integers. So actually these two graphs that are very different as graphs, one has cycle, the other doesn't have cycle. So that's in graph world, that's huge difference. So these two very different graphs actually have a Grothendieck group that is the same, Z in both cases. So you see, that's why we need grading, because this is not a very, very big of a distinction, right? There is just, you know, same group in both cases. So that's why we need graded. And before we go to grading, let's maybe do just one more example, which is the rows. Let's call it 3, the rows. And if you remember, we computed a Grothendieck group of this algebra, so it better be 0, right? So if you remember, when, on Monday, we said that if R is such that R plus R is isomorphic to R, then we computed K0 of R to be 0, right? So here we better get that 0 also. So let's see how many relations, how many generators. So I still have one generator only. And I have one relation. And that relation is telling you that V plus V is equal to V plus V, right? Because this one and only vertex, which is regular, is equal to the sum of ranges of all edges that it emits. So it emits two edges, right? So here I will have range of first, V, range of second, V. So this one and only relation here is that V is equal to V plus V. But when you complete to a group, you need to make this monoid cancelative, right? Because that group, I mean, this is not cancelative because this holds, right, in the monoid. But when I complete to Grothendieck group, I need to make my monoid cancelative, and then I add all the inverses. So in the process of making this cancelative, I can cancel this, right? So in K0 of this Leavitt path algebra, V is equal to 0. So that means that your one and only generator is equal to 0, right? So that means that the whole group is going to be 0. So this also indicates a need for graded rings because this graph is far from trivial, right? And Grothendieck group of this graph is still 0. So that's why if you, I'm not sure. I'm not sure if you get a printout of my notes or if you had a chance to look at them yet. But on the page, when I'm introducing graded rings, I put a knight in shining armor that comes to save the day. So that's how graded rings are in this situation. They are really coming here to save the day. So because this K0 is, as you have seen, super possible to compute, right? We just have to play with that relation and how many generators we have, and then we compute it. So that's all nice and well, but this Grothendieck group is not that telling of Leavitt path algebra. So that's why graded rings come to rescue the day. And so let me spend these last 15 minutes of today just giving you some background of what graded ring is, and then we will be able to compute a graded version of Grothendieck group. And the conjecture pretty much tells that this graded version of Grothendieck group is classifying Leavitt path algebras completely. So two Leavitt path algebras are isomorphic as graded algebras if and only if their graded version of Grothendieck group is isomorphic to each other. So you see, because of the words graded in this conjecture, that's why we need a little bit background on graded rings. So what is a graded ring? It's a ring, let's say R, such that you can chop it in pieces. And I want you to think, okay, this is my graded ring R, and somehow I can chop it in pieces. And each piece I am indexing by group. So I should say ring graded by group gamma. So you can chop it in pieces, and you can index each piece with element from a group. So when you add all those pieces up, you have the whole ring. It's a direct sum, meaning that these two pieces intersect only at 0, right? So you can chop it in pieces like this. And you want to do it in such a way that when you take element from here, from gamma piece, and when you take element here from delta piece, let's say, and when you multiply them, you are going to end up exactly at piece that corresponds to gamma times delta. So this is your graded ring now, right? It is chopped in pieces. And when you take two elements from two pieces and when you multiply them, you end up in a piece that actually corresponds to the product. How can you write that down? So R gamma times R delta is contained in R gamma delta. So that's what a graded ring is. Let's do examples before we go any further with graded rings. So let's do some examples. So our group gamma for Leavitt Graph algebra is going to be a group of integers. And that's why in all my examples, we are always going to have gamma being group of integers. For Leavitt Graph, my third example is Leavitt Graph algebra. But let me first give you how you can grade that ring of Laurent polynomials. As we have seen, that appears in a lot of places, right? And I also want you to be comfortable with Laurent polynomials for another reason that is coming up soon. So let me take Laurent polynomials and let me give you what I call the natural grading. So if I tell you about grading, that means that pretty much I need to tell you what is the nth component for any integer n, right? So in that nth component, I want you to have k multiples of only x on n. What are these Laurent polynomials? These Laurent polynomials are like polynomials, like good old polynomials, except that your x can have negative powers as well, right? So for example, if I have polynomial 2x to negative 2 plus x minus 3x cubed, then this element here is going to be negative 2 component. This element here is going to be in 1 component that corresponds to 1, and this element here is going to be in a 3 component, in component that corresponds to 3, right? So in a way, it's natural, right? You know, take polynomial and look at each monomial, and then that monomial is in some component, and that's why this holds, because every element of this I can chop in pieces, right? And I can tell in which component each piece is. And why does this hold? Because this pretty much holds because x on n times x on m is equal to x on n plus m, right? That's why this holds. So it's all good. It is a grading. For my second example, let me give you the same ring. But let me now have it with trivial grading. This grading we will also have to understand for another reason that is coming very soon tomorrow. But let me just tell you what a trivial grading is. So trivial grading is, I want you again to think of our kind of chopping in pieces here. So, and again, my gamma is going to be integers. So I want you to think that these pieces here correspond to like 0, -1, -2, 1, 2, and so on. So trivial grading is when you put everything in 0 component and nothing anywhere else. Every ring can be graded trivially by any group. That always works, right? Because just think about it. Every ring can be graded trivially by every group. And in particular, this ring here can be trivially graded like this. So I want you to think that these two are kind of, you know, two extremes in a way. So in this version here, here I have k, here I have k on x on 1, kx squared, kx negative 1. So everywhere I have something. And here I put my, all in in one spot. So that's why they are kind of, opposite, two extremes in a way. And now let's take a look at the third and most important example, which is Leavitt path algebra. So remember how we were saying at the very end of last class that every element can be written like this, right? Is a finite sum of k's from my base field, and pq stars are paths and ghost path. Remember how we were saying that you can always do that because somehow that ck1 allows you to push stars always to the back. So pretty much if I tell you what's the grading of this element, in which box I'm going to put this element, then I know how to handle the whole algebra, right? And these numbers that I'm assigning to these elements of the ring, that's also called the degree. So pretty much I need to tell you what is degree of this element, right? So that degree of this PQ star is going to be length of P minus length of Q. So this here is length. So you see P is kind of real path, right? So it has a length. And so this, think of that P having some length of P. And Q, I want you to think that they end in the same way so that I can compose P and Q star. So because I'm kind of going backwards with Q, because it's starred, that's why I have minus length of Q. So every element of Leavitt path algebra, I can chop in pieces like this. And for each piece, I can assign integer value to it. And that integer value gives me the grading. So you see, that's why the integers are important for Leavitt path algebra, because of lengths of paths. So if I have a path, a natural number that I should assign to it is how long it is. And if I have these ghost paths kind of going back, the natural number that I should assign to it is negative of the length of path. And that's why if I have PQ star, then it's going to be length of P minus length of Q. So before we go further with graded rings tomorrow, before we go further with graded rings tomorrow, I will just tell you about how the world of graded rings look like. So how you obtain definitions in world of graded rings, having the good old definitions about rings, available. So the name of the game is take your definition that defines something in ring. When is ring regular? When is ring a field? When is ring Noetherian? Whatever you want. And replace every element with homogeneous element. So for every element, for example, definition says for every element something happens. If you want the graded version of that definition, you are going to say for every homogeneous element something happens. And I didn't tell you what is homogeneous. Let me do that next. So every element you are replacing with homogeneous element. And what is a homogeneous element? Element from one of these components. So think about this example with Laurent polynomial that I actually can still see here on my smudgy board. So that polynomial that had three terms itself is not a homogeneous element because it consists of elements from different components. But each of these monomials is homogeneous. So elements from R are sum of some elements from here. But elements from here, from each component, they are homogeneous. In Leavitt path algebras, these would be homogeneous elements, right? So let me give you an example of this, bizarre world of graded rings type of rules. So, for example, when is a ring a field? If it's commutative and if everything has inverse, right? So let's talk about the inverse. Let's forget about commutative. So that would then be not a field, but division ring. When is ring a division ring? If for every x not equal to 0, x has inverse, right? So if you want to define a graded division ring, you are going to say that something is a graded division ring if it's graded, and for every x not equal to 0 and homogeneous, x has inverse. So let me give you one example that is hopefully going to illustrate why that is good. Why we will, in a way, have more freedom with graded rings. They're certainly more general than all rings. Because as I said, every ring you can grade trivially by any group, and then everything is homogeneous with trivial grading. So certainly this is equivalent, right? So that's why I want you to perceive graded rings both as a generalization of all rings, but also as a more freeing concept. Because let's, for example, look at these Laurent polynomials. They are not division ring. They are not field. This is commutative, so division ring, field, same thing. So they are not division ring because pretty much this, for example, element, it's not 0, but it doesn't have inverse. Right? So this is certainly not a division ring. However, with natural grading, this is a graded division ring. Because now we don't have to require that x has inverse for every non-zero x, but only for monomials. And monomials do have inverse. Let's take a monomial. I should say non-zero. So if I take a monomial, it looks like something from the field times power of x, right? This is how a monomial looks like. These are homogeneous elements. That's how homogeneous elements of this ring with natural grading, how they look like. So if this is not 0, that means pretty much that k is not 0, right? And since k is a field, it has k inverse, right? I mean, this lowercase k has inverse. And x on n certainly has inverse, right? Doesn't it? So you have x on negative n, and that is inverse for that, and every monomial has an inverse. So you see, if you're thinking of these no-exit graphs that are matrices over a field and plus matrices over not a field, when we are looking at non-graded Leavitt path algebras, I mean, when we look at Leavitt path algebras as without the grading, then we have that these Laurent polynomials may not necessarily be division rings. But if you look at that with graded in your mind, then actually this is a graded division ring. So it is a graded field. It's commutative, so it is graded field. So all these matrix algebras that we have been looking at as graded rings, they are actually taken over fields, which is way, way nicer. So let me stop with this introduction to graded rings here. We will finish this tomorrow. And then actually we will already be able to compute Grothendieck group of, or in this sense, with the grading of a bunch of Leavitt path algebras. And then, you know, conjecture is there in front of us almost. How are we doing with this portion? Do we have some questions? Are we iffy about something?
Leah, in the part when it involves matrix and the matrix parts of the Leavitt path algebra, you will be using that grading which involves the diagonals and upper diagonals and lower diagonals of the matrix.
You mean the incidence matrix?
In the matrix part, if the Leavitt Leavitt algebra has a matrix component, what is the grading you could use in that part, or you don't use it at all?
So actually, that is why we need a little bit more background, because that's coming up tomorrow at the beginning. So remember how, let's say that we have a sink and nothing else, right? So then your Leavitt path algebra is isomorphic to something like this, right? So this end here tells you how many paths end in that sink, right? Maybe you can have something like this. So it tells you how many paths altogether end at that sink. If you consider the grading, then you can do a little bit more fine-tuning, because graded matrix algebras come with some sort of integer values here. So that's what I need to tell you about, right? All matrix algebras considered as graded rings, they come equipped with some array of integers after the name of the algebra. So I need to tell you what that is. And for Leavitt path algebras, this is how many paths, and these would be the lengths of those paths. So let me just do one last example really quick. Our favorite one, this one, and this one here, right? So as non-graded rings, these two Leavitt path algebras are isomorphic, because here we have one sink, here we have three paths ending there, 0, 1, and 2. So 3 paths all together, that's it. But here we also have 3 paths, right? 0, length 0, this one and that one. So that's also 3. So you see, as graphs, these two graphs are not very much, you know, similar to each other. I mean, as graphs, they are different. This one has one vertex that receives 2 edges. This one doesn't have such a vertex. It doesn't have a vertex that receives 2 edges, right? So as graphs, they are different. This one has 1 source. This one has 2 sources. So as graphs, they are different. But Leavitt path algebras are still the same, right? So that means that without grading, even Leavitt path algebras cannot really tell the graphs apart. But when we look at these two things as graded algebras, then we incorporate the lengths of these 3 paths. So that's length 0, length 1, and length 2. And here it is length 0, length 1, and length 1. So as graded algebras, they are already different. So that's pretty much what's coming next, right? I need to tell you what this means, right? What does it mean when I write n numbers after matrix algebra? And that's the part for which we need that background on graded rings. But once when we go over that, then it's actually fun again, because then we can just compute stuff and understand what we are computing.
Thank you very much.
Oh, sure. Actually, these chats, these are my favorite parts, where it's not just me that I talk, but I get some feedback from you. So if you have a question, just ask.
Hello. Hi,
Hi.
Leah. I hope you can see me.
I'll be honest with you, not really well, but I know you're there.
This is Alfie.
Hi.
I believe a known results tells us that if we have a graph that has like more than one component, then the Leavitt path algebra is a direct sum of those components. I think that's from Abrams, if I'm not mistaken. And then we have learned today that even if if the graph is only one component, then the Leavitt path algebra could be a direct sum of matrix and the Laurent polynomial. Is it then safe to say that the number of components does not play as much role as what we could hope for in the classification of Leavitt path algebra?
It's definitely not if and only if. So if there are n components, then there will be direct sum of at least n things. But each of these components can still be taken apart. So for example, let's take the kind of the opposite of this ring. This one has two sources, one sink. Let's take a look at the other way around. Two sinks and one source, right? So this already will be direct sum, right? Because this is no exit, it has two sinks. So you are going to say, aha, there are two sinks, so I will say there are at least two m's, right? So this one has 0 and 1, so 2. And this one also has 2. So the converse doesn't hold. So if there are n components, there is at least n summands, but the converse doesn't hold, that if there are n summands, then there are n components. But however, you know what is a good brain teaser? Think about how and why in the non-graded world this and this will be isomorphic, right? Because here you have two components, and each of these components, when I look at it on its own, it is one sink and two paths ending there. So it's this, right? And then this is also one sink and two paths ending there. So you can play with something like this. So in the non-graded world, that's the same. We will see how and why we can differentiate their K0s in the graded world, right? We will use something that is called pointed K0. So if you remember at the very, 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 very beginning of Monday's class, when I stated the conjecture, I said two Leavitt path algebras are isomorphic if and only if their K0s are isomorphic as pointed groups. So when you we will talk about pointed on Friday, probably not before, but when you consider these two with that pointed business, then you can tell them apart. So their K0 can tell them apart.
Okay, thank you, Leah.
Sure.
Any other question? Oh, if not, thank you very much, Leah.
So I will see you soon again, right? In the question section today, I will see you all again. And then actually, I like that because then we will be able to chat some more.
Right, in 2 hours and 45 minutes, I think.
Yeah. So have a good lunch, and then I'll see you later.
All right, bye-bye.
Bye.